Welcome to the third installment in the video series on electron configuration. The goal of this video is to demonstrate how electron configuration can be used to explain the structure of the periodic table and as an entryway to start describing the physical and chemical properties of the elements. As a starting place, what we're going to do together is practice an electron configuration on magnesium. So we see that magnesium has an atomic number of 12, which means that it has 12 protons, and in the neutral atom that means it also has 12 electrons. So its electron configuration is going to be 1s2, 2s2, 2p6, 3s2. We go back and we count electrons to make sure that we've used the right amount, and we see that we have 2 electrons in energy level 1. We have 8 electrons in energy level 2 for a total of 10, and 2 electrons in energy level, in the s orbital of energy level 3. So the electron configuration is correct. All right, what I want to do now is practice some electron configurations, but we're going to do it by group. So we're going to start with group 1A, which is on the far left side of the periodic table. The red numbers that I indicated to the left of the symbols represent period number, and as we go through this, what I want you to do is think about the relationship between the group number and the period number. Remember that the group number is a reference to valence, which is the number of electrons in the outermost energy level of a particular atom, or another way of thinking about it, it's the number of electrons on the outer surface of a particular element. The period number tells us which energy level is being filled. All right. So what we're going to do is we'll complete the electron configurations of these elements, and then when we're through, we'll look at the various patterns and try to make sense out of what we're seeing. So we're going to start with hydrogen. Hydrogen has 1 electron, so its electron configuration is 1s1. Lithium's next, has 3 protons, therefore it has 3 electrons, and its configuration will be 1s2, 2s1. Sodium has 11 electrons. Its configuration will be 1s2, 2s2, 2p6, 3s1. Potassium has 19 electrons, so let's take a look at its configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. All right, now what I want to draw your attention to is back to the group number. The group number is valence. So if we look at the configuration of each one of these elements as we move down the group and we identify the outer shell electrons, we see that for hydrogen, this is the outer shell because quite simply there are no other electrons. In the case of lithium, we see that energy level 1 is completely full. So I'm going to underline the valence, and we see for lithium it's 2s1. For sodium, similarly, energy level 1 is full, energy level 2 is full, so this is the outer valence for sodium, 3s1. And then finally, in potassium, we see that the first 3 energy levels are full, the outer valence is 4s1. All right, now we're going to turn our attention to group 2A, and we're only going to do the first 3 elements of 2A. Again, the red number to the left is the energy level or period number, and the number at the top is the group number or the valence. So let's look at beryllium first. It has 4 electrons, so its electron configuration will be 1s2, 2s2. Magnesium, 12 electrons, 1s2, 2s2, 2p6, 3s2. And then calcium, which has 20 electrons, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. All right, again, what we want to focus on here is the outer shell. Now, one mistake that students usually make when we address the elements in group 2A, or the electron configurations of the elements in 2A, is when they look at the outer shell, they think because there are 2 electrons in the 2s that means energy level 2 is full. But you need to remember that energy level 2 actually has 2 sets of orbitals, the 2s and the 2p. So beryllium beryllium's energy level 2 is not full. This, in fact, is the outer valence. When we look at magnesium, we see a similar situation. Energy level 1 is full, energy level 2 is full. This is the outer valence of magnesium, the 2 electrons in the 3s. And by the same token, the 2 electrons for calcium that are in the 4s shell. Energy level 1 is full, energy level 2 and energy level 3 are completely full. Now, what we're going to do next is skip all the way across the periodic table to group 3A. So we're basically skipping over the transition metals. In group 3A, we're only going to focus on the first 2 elements in the group. That's going to be boron and aluminum. Again, the red numbers to the left indicate period number. So boron is in period 2 and aluminum is in period 3. Okay, the electron configuration for boron is going to be 1s2, 2s2. All right, let's see how many electrons we've used. This is a total of 4. So we have 1 left, and it will go into the p shell. All right, so the electron configuration for boron is 1s2, 2s2, 2p1. Similarly, for aluminum, we have 13 electrons, so its configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p1. All right, so let's just confirm we used the right number of electrons. We have 2 electrons in energy level 1, 8 electrons in energy level 2 for a grand total of 10, and then there are 3 electrons in energy level 3 for a total of 13. All right, like we did in the last examples, what I want to do now is address the outer shell. Things get a little tricky here because remember that in energy level 2, for example, you have 2 suborbitals, the s and the p series. So the outer shell for boron is actually this whole collection, a total of 3 electrons. The 3 electrons that are in energy level 2. And for aluminum, energy level 1 is full, energy level 2 is full. This would be the outer valence for aluminum. So the outer valence for the elements that we're going to now do between group 3 and group 8 will involve 2 suborbitals. All right, we're going to move to the right now into group 4A, and we're only going to deal with 2 elements in group 4A, carbon and silicon. Again, the red numbers to the left are period numbers, and the number at the top is the group number. All right, so let's do the configuration for carbon. There are 6 electrons, so it's going to be 1s2, 2s2, 2p2. All right, and then in the case of silicon, we have 14 electrons, so it's going to be 1s2, 2s2, 2p6, 3s2, and 3p2. All right, and then like in the last series, we're going to identify the outer shell. There should be 4 electrons in the outermost energy level of both of these elements. We see for carbon, that will be this set of suborbitals here, the 2s2, 2p2, and for silicon, it'll be 3s2, 3p2. So this is the outer valence of silicon, and this is the outer valence of carbon. All right, so now let's take a look at group 5A. We're only going to focus on 2 elements, nitrogen and phosphorus. The red numbers again are period number. The number at the top is the group number. It tells us the valence, how many electrons we should have in that outer shell. So let's start with nitrogen. We have 1s2, 2s2, 2p. Okay, what do we do? We've got a total of 4 electrons already placed. That means we have 3 to go. So there should be a 3 in the p. So its configurations 1s2, 2s2, 2p3. A grand total of 5 in the outer shell. All right, for phosphorus, the configuration will be 1s2, 2s2, 2p6, 3s2, and 3p3. Almost made a mistake, 3p3. All right, now let's look at our outer valence. For nitrogen, it's 2s2, 2p3, total of 5. And for phosphorus, it's 3s2, 3p3. All right, group 6A. Configuration for oxygen. 1s2, 2s2, 2p4. We add the 4 to the 2, that's a grand total of 6, and then 2 more, that's 8. All right, we're going to move a little faster now. Hopefully you've caught on to the patterns. So this is going to be our outer valence right there for oxygen. All right, now for sulfur, we have 16 electrons, so it's 1s2, 2s2, 2p6, 3s2, 3p4. And the outer shell for sulfur is right here. All right, now group 7a. All right, fluorine and chlorine. So the electron configuration for fluorine is going to be 1s2, 2s2, 2p5. 5 and 2 is 7, and 2 is 9. The outer shell is this configuration here. For chlorine, we have 1s2, 2s2, 2p6, 3s2, and then 3p5. The outer shell here. All right, and then finally into group A. Now I've added an extra element here because in group 8A we also have a period 1 element at the very top, which is helium, and we've dealt with helium before. That's no big surprise. So we're going to do helium, neon, and argon. Now as we move left to right across the table, hopefully you observed in the examples we've been doing that we've been progressively filling whatever energy level that we're in. And now in group 8A we're going to see that these shells are completely full. So starting with helium, the configuration is going to be 1s2. Its outer shell is literally just its configuration because it has no other electrons. In neon, the configuration will be 1s2, 2s2, 2p6. The outer shell is here, and you see it's completely full. So group 8A has elements in it that have completely full energy levels. And I'm going to come back to what the ramifications are for this in terms of their physical and chemical properties later. Now let's take a look at argon. It has 18 electrons, so it's 1s2, 2s2, 2p6, 3s2, 3p6. So we see that energy level 3 for argon is completely full. All right. Now, what I want to do before we close is talk about the pattern that we've been looking at. So here we're looking at a periodic table, a blank periodic table in which all I've done is put information about which orbitals we've been filling. So for example, we started with group 1A, which has hydrogen at its top. The next element down would be lithium, all right, then sodium, and then potassium. And in group 2A, we started with beryllium, and then we moved down to magnesium and then to calcium. And the take-home message here for group 1A and group 2A is that we were progressively filling s orbitals. So we call this part of the periodic table the s block. All right, now we're going to skip all the way across the table to group 3A through 8A. And in this case, you'll notice that we started out group 3A with boron. And the first electron in boron after the 2s suborbital went into the p shell. So we call this part of the periodic table the p block, because when you go back and review what it is we did, we systematically filled the p shell as we move left to right into group 8A. And then we didn't really do any examples of this yet, but the middle of the table, the transition metals, we call a d block, because here when we start filling, and the first element that's going to appear in period 4 here is going to be scandium. And when we start filling scandium's electronic configuration, what you're going to see when we do that is literally we're going to be filling the d shell as we move across here. So the periodic table can be broken down into some blocks. This will help you think about how to fill electron configuration. We have the s block, the d block, and the p block.